Hello everyone, let's go ahead and take a look at definite integrals using the u-substitution part 2. Now part 1 was just dealing with indefinite integrals. With part 2, what we're going to look at is how to actually integrate definite integrals using the u-substitution method. Now here we have a typical definite integral, and what we're going to do is we're going to use the u-substitution. So let u be equal to 2x minus 3. d of u over d of x is equal to 2, so therefore d of u is equal to 2 d of x. Now all I want is d of x by itself, so I'll multiply both sides by 1/2. And I come out with d of x is equal to negative 1/2 d of u. So what happens then is, one thing that you have to be careful of is that these lower and upper bounds for the limits of integration are actually x values. So what I'm going to do right now is I'm going to make sure that that is very clear, that those are x values. Then I'm going to go about doing the u-substitution here. So notice what I come up with is 1 over u times 1/2 d of u. The 1/2 in front, because that's just a scalar multiple. Integral from x is equal to 3 to x is equal to 6 from 1 over u d of u. We all know that that's going to be the natural log of the absolute value of u. Now, usually what happens at this point is, with the fundamental theorem of calculus, I can just go ahead and do the substitution at this point. But I cannot, because of the fact that these are x values and that's a u. So the first thing that needs to happen is I need to change this back into its x value. So u, again over here, was equal to 2x minus 3, which is that. Then I can go ahead and do the substitution now. So I have 1/2, the natural log of the absolute value. If I substitute the 6 here, that's 12 minus 3, which is 9. Minus, if I go ahead and substitute that here, I get the natural log of 3, which is right there, the absolute value of 3. So now I can go ahead and simplify this. 1/2, that's the natural log of 9 minus the natural log of 3. That's the same thing as 1/2 the natural log of 9 over 3, which is 1/2 the natural log of 3. Okay, so everything should be pretty clear there as to how we go about evaluating a definite integral when we're using the u-substitution. Now there's another way that you can approach this with, which might actually make things simpler and make the calculations much more easy to do. So say, for example, here's the exact same integral that I have. And notice I'm doing the exact same substitution here that I would have here. The only thing that I'm going to do differently is that instead of actually keeping these as x, I'm actually going to change them to u values as well, because I know what the relationship is between u and x. So what I say then is that if this upper bound is 6, if I substitute the 6 in here, then I know that the upper bound for u has to be 9. I would do the same thing for x is equal to 3. If I substitute that, then u has to be equal to 3. So notice what happens then is that if I take this original definite integral, using the u-substitution, I can change everything, including the limits of integration, to u values. Okay? And notice that what happens then is I have 1/2 the integral of 3 to 9 of 1 over u d of u. That, of course, is 1/2 the natural log of the absolute value of u from 9 to 3. And then I just substitute in, and I come up with the natural log of 9 minus the natural log of 3, which is, of course, 1/2 natural log of 3. So notice that you're coming out with consistent results. One, in this case over here, you're substituting back into x and then substituting your limits of integration. Here you're actually calculating changing the limits of integration from x values to u values, so that when you come down here, you can do a straight substitution. So whichever way that you want to approach these two is up to you. I think this one will probably be a little bit easier because your calculations are going to be simpler. Okay? Let's just do one more just to be on the safe side, to make sure that everybody's clear as to how to work these out. Okay, let's see if you can do this one. Okay, this one says you have the integral from 0 to 1 of x squared e to the x cubed plus 1 power d of x. Okay, so it's pretty clear, I think, that we need to let u be equal to x cubed plus 1. And that means that d of u over d of x is going to be equal to 3x squared d of x. So d of u is going to be equal to 3x squared d of x. Oops, sorry. 3x squared d of x. And then we need the x squared d of x, so that's just going to be 1/3 d of u is equal to x squared d of x. Now, I'm going to go ahead and change those values. For me, it's simpler to do it at this step. So if x is equal to 1, then u then becomes, so if I go ahead and put that in there, u then becomes 2. If x is equal to 0, then u becomes 1. Okay, and then what I'll do then is change everything into u values. So what I have here is the lower limit is 1, u is equal to 1, to the upper limit, which is u is equal to 2. This is going to be e to the u times it by, and the x squared d of x is giving me 1/3 d of u. 1/3 d of u. So what I come up with then is 1/3 times the integral from 1, oops. Now that I know that these are u values, I don't have to write u. 1 to 2 of e to the u d of u, which of course is going to be just 1/3 e to the u evaluated from 1 to 2. So therefore I can now use my fundamental theorem of calculus to say that this is 1/3 times it by e to the second minus e to the first. Okay, so there you go. 1/3 e to the second minus e. And there you go. And you come up with your answer for this particular definite integral using u-substitution and changing the limits of integration to u values so that you can just go ahead and evaluate using the fundamental theorem of calculus in just one step. Okay, and there you go. There's your definite integrals, the u-substitution part 2. We'll go ahead and take a look at some examples again in class. Hopefully this makes sense. Okay, so good luck. We'll see you next time. Bye-bye.